Hello friends, welcome to my lecture on uniform convergence of a power series. We have already discussed that when the series power series converges uniformly, the sum function of the power series is a continuous function. Now as regards the term by term and also we discussed the integration term by term of a power series. So as regards the term by term differentiation of a power series, we have the following result. If f x equal to sigma n equal to 0 to infinity, C n x minus a to the power n converges for mod of x minus a less than r, then the series sigma n equal to 1 to infinity n C n x minus a to the power n minus 1 has precisely the same radius of convergence. So this series you can see sigma n equal to 1 to infinity n C n x minus a to the power n minus 1 has been obtained by term by term differentiation of the series sigma n equal to 0 to infinity C n x minus a to the power n. So precisely what we are saying is that if the given series has radius of convergence r, then the differentiated series also has the radius of convergence r. So let us prove this result. Let us take a arbitrary point x naught and let us fix it. So let x naught be an arbitrary but fixed point such that 0 is less than mod of x minus x naught minus a less than r, and then choose a point x such that mod of x minus a is less than mod of x naught minus a less than r. Now the convergence of the series sigma n equal to 0 to infinity C n x minus a raised to the power n for mod of x minus a less than r, because we have assumed that the series sigma n equal to 0 to infinity C n x minus a to the power n has radius of convergence r. So the region of convergence for this series is given by the inequality mod of x minus a less than r. So the convergence of this series for the region mod of x naught x minus a less than r implies that the series sigma n equal to 0 to infinity C n x naught minus a to the power n is convergent. Now let us see how we get this. You have x naught is a point which belongs to this interval, okay, which belongs to the region mod of x minus a less than r. So what we have, the convergence of this implies that sigma n equal to 0 to infinity C n x naught minus a raised to the power n is a convergent series. The convergence of sigma n equal to 0 to infinity C n x minus a to the power n for mod of x minus a less than r implies that the series sigma n equal to 0 to infinity C n x naught minus a to the power n is convergent, because x naught belongs to this interval a minus r to a plus r by our hypothesis. Okay. Now since this series is convergent, okay, we know that for an infinite series the convergence of an infinite series implies that the nth term of the series goes to 0. So this will imply that limit n tends to infinity C n x naught minus a raised to the power n equal to 0. The nth term of the series goes to 0, that is the necessary condition for the convergence of an infinite series. Now let us look at this sequence C n x naught minus a to the power n. The limit of this sequence as n goes to infinity is 0 implies that the sequence is bounded. So we can find a constant a greater than 0 such that C n times x naught minus a to the power n mod of that is less than or equal to a. So, okay. So this implies that the sequence x naught minus a raised to the power n is a bounded sequence. So by the definition of a bounded sequence, we can find a constant a greater than 0 such that mod of C n x naught minus a to the power n is less than or equal to a for all n belonging to n. Now let us choose a real number x such that mod of x minus a over mod of x naught minus a, we assume this ratio to be rho, then from this inequality mod of x minus a less than mod of x naught minus a, it follows that rho is less than 1. Now when rho is less than 1, we get this inequality, mod of n c n x minus a to the power n minus 1 is less than or equal to n into a rho to the power n minus 1 into x naught minus a mod. Okay. So, let us see how we get this. So, n c n x minus a to the power n we can write as n c n x minus a to the power n into x naught minus a to the power n divided by x naught minus a to the power n, and this I can write as n c n into x naught minus a to the power n, and then we have x naught minus a here, and we get here x minus a to the power we have x n c n x minus a to the power n c n x minus a, and we get n c n over x naught minus a to the power n minus 1. So, we have this n c n x minus a to the power n minus 1 we have okay. So, n c n x minus a to the power n minus 1 we have. So, we take n minus 1 here. Okay. Yeah. So, we have n c n x minus a to the power n minus 1 equal to n c n x minus a to the power n minus 1. Now, we multiply and divide by x naught minus a to the power n, and then collect n c n into x naught minus a to the power n, because for this we have the inequality. Okay. We have the inequality that c n times x naught minus a to the power n this is less than or equal to a. So, what do we get? Now, let us see, this will be, so mod of this, okay, mod of this is equal to mod of this, okay, and then we get mod of this, mod of this. So, let us take what I mean is that you take the mod of n c n x minus a to the power n minus 1 n c n into x minus a to the power n minus 1, then you get mod of n c n x minus a to the power n minus 1 mod x naught minus a to the power n over x naught minus a to the power n, and you get mod of n c n x naught minus a to the power n over mod of x naught minus a, and this is x minus a. Okay. Now, this is what this is equal to mod of n c n x naught minus a raised to the power n over mod of x naught minus a, and this is equal to rho, this is rho. Okay. So, rho to the power n minus 1, okay, and rho is less than 1, and mod of n c n x naught minus a. So, mod of c n x naught minus a to the power n is less than or equal to a. So, this is n into a divided by mod of x naught minus a into rho to the power n minus 1. Okay. So, what we get, mod of n c n x naught mod of n c n x minus a to the power n minus 1 is less than n into a less than or equal to less than or equal to, okay, less than or equal to mod of n into a rho to the power n minus 1 over mod of x naught minus a. Okay. This is rho to the power n minus 1, okay, and mod of c n into x naught minus a raised to the power n is less than or equal to a. So, this is less than or equal to n into a mod of x naught minus a into rho to the power n minus 1. Now, what we do? Now, this let us look at the convergence of this series, sigma n equal to 1 to infinity n into a rho to the power n minus 1 mod of x naught minus a. Okay. The convergence of this implies that, now why it is convergent, you can apply ratio test. So, limit n tends to infinity, let us apply the ratio test. So, limit n tends to infinity mod of c n plus 1. So, that means mod of n plus 1 into a into rho to the power n divided by mod of x naught minus a into mod of x naught minus a divided by n into a rho to the power n minus 1. Okay. So, mod of x naught minus a will cancel with mod of x naught minus a will cancel, okay. Rho to the power n minus 1 when divides rho to the power n, you get rho, and n plus 1 over n. Okay. So, what we get is limit n tends to infinity n plus 1 by n into rho, which is equal to rho, and rho is less than 1. Okay. So, the limit exists. Okay. So, the limit exists and is less than 1. Okay. So, this means that this series by ratio test, it is convergent. Now, when this series is convergent, the series sigma n equal to 1 to infinity n c n x minus a to the power n minus 1 converges uniformly, okay, by Weierstrass test for mod of x naught minus a less than mod of x naught minus a. Okay. So, since x naught is arbitrary, okay, with 0 less than mod of x naught minus a less than r, the series sigma n equal to 1 to infinity n c n x minus a to the power n minus 1 converges uniformly for mod of x minus a less than r. Now, let us take, okay. So, when this series differentiated series converges uniformly for a mod of x naught x minus a less than r, we can say that if r dash is its radius of convergence, then r dash must be at least r. Okay. So, r dash must be greater than or equal to r. Now, if the radius of convergence r of the given series is infinity, then since r dash is greater than or equal to r dash is also infinity, and so r is equal to r dash, and therefore, the theorem is proved. Okay. So, in the other case, let us take r dash to be greater than r. Okay. Our aim is to show that r dash is equal to r. So, when r dash is greater than r, let us choose a point x such that r is less than mod of x minus a less than r dash. Then for this x, okay, since the radius of convergence of the differentiated series is r dash, okay, sigma n equal to 1 to infinity n c n x minus a to the power n minus 1 converges absolutely, while the series sigma n equal to 0 to infinity c n x minus a to the power n diverges, because its radius of convergence is r. Okay. And the point x lies outside the circle of convergence or the region of convergence, because we are assuming mod of x minus a greater than r. So, then mod of c n x minus a to the power n. Now, let us look at this. We want to arrive at a contradiction. Okay. So, mod of c n x minus a to the power n we can write as n c n x minus a to the power n minus 1 into mod of x minus a over n. Okay. Now, this is less than or equal to n c n x minus a to the power n minus 1 as soon as mod of x minus a over n is less than 1. So, we have already chosen a point x such that r is less than mod of x minus a less than r. Okay. Now, let us take n to be so large that mod of x minus a over n becomes less than 1. Then for such a n, okay, what do we notice? Mod of c n x minus a to the power n is less than or equal to n c n x minus a to the power n minus 1. So, by comparison test, okay, since the series sigma n c n x minus a to the power n minus 1 is convergent, the series sigma c n x minus a to the power n is also convergent, but that is clearly a contradiction, because the series sigma n equal to 0 to infinity c n x minus a to the power n diverges for a x which is mod of x minus, which satisfies mod of x minus a greater than r. Okay. So, the sigma n equal to 0 to infinity c n x minus x naught minus a to the power n converges. For this x, sigma n equal to 0 to infinity c n x minus a to the power n converges for this x, which is false, and hence r dash should be equal to r. So, that is how we prove this theorem. Now, under the same hypothesis, okay. So, what we have now, the series sigma n equal to 0 to infinity c n x minus a to the power n, we have seen if it has radius of convergence r, then the differentiated series also has radius of convergence. The sum function of that will then be f dash x. Okay. So, when we assume that if we have an infinite series sigma n equal to 0 to infinity c n x minus a to the power n with radius of convergence r, then the differentiated series also has same radius of convergence, and the sum function which was f x, now it will be f dash x. Okay. So, let us say let f x be sigma n equal to 0 to infinity c n x minus a to the power n, it converges in the region mod of x minus a less than r. Then by induction we can say, because we have seen that f dash x is equal to sigma n equal to 0 to infinity c n x minus a to the power n. Okay. The f has derivatives of all orders, and the kth derivative of f is obtained by differentiating the infinite series sigma n equal to 0 to infinity c n x minus a to the power n term by term k times. All the derived series have the same radius of convergence. So, this using mathematical induction on n, we get this corollary. Okay. So, now let us read give a remark. If the radius of convergence of the power series is infinite, suppose the series converges for all values of x, okay, then the convergence is not necessarily uniform on the entire line. We have said that if the series has radius of convergence r, and then the region of convergence is given by mod of x minus a less than r, then the differentiated series also has the same radius of convergence, that it says that it also converges in the same region mod of x minus a less than r. So, this convergence is not uniform on the entire line, okay, but it will be uniform on a any closed interval. Okay. So, there exists this remark which we have to notice. Now, a function f defined in some interval by a convergent power series is called an analytic function. Okay. So, the definition of an analytic function is that it should be defined in some interval by a convergent power series. Now, if f is analytic, then the power series representing f is known as the Taylor series. Let us say if we have two functions f x sigma n equal to 0 to infinity a n x to the power n and g x sigma n equal to 0 to infinity b n x to the power n are analytic, okay, then the sigma n equal to 0 to infinity a n x to the power n is the Taylor series of f. Okay. Then sigma n equal to 0 to infinity a n x to the power n is the Taylor series of f. Okay. So, a n must be equal to f n 0 over n factorial, okay, and sigma n equal to 0 to infinity b n x to the power n is the Taylor series of the function g. So, b n must be equal to g n 0 by n factorial. Okay. So, if two functions f x and g x are analytic and f n 0 is equal to g n 0. So, when f n 0 is equal to g n 0, okay, then a n will be equal to b n for all n, okay, equal to 0, 1, 2, 3 and so on. Okay. And so, the two functions f x and g x will be same. Now, vanishing of all coefficients. If a power series has a positive radius of convergence and a sum that is identically 0 throughout the interval of convergence. So, let us consider the power series sigma n equal to 0 to infinity c n x minus a raised to the power n, which has a positive radius of convergence, say r, and its region of convergence is, let us say, is given by mod of x minus a less than r. The sum of the series is suppose f x, then we have f x equal to sigma n equal to 0 to infinity Cn x minus a raised to the power n. Now it is given that the sum is identically 0 throughout its interval of convergence. So f x is equal to 0. We are given f x equal to 0 for all x satisfying a mod of x minus a less than r. Okay. Now Cn's are given by f n a over n factorial for all n equal to 0, 1, 2 and so on up to infinity. Okay. So since f x equal to 0, okay, for all x, we have f n a equal to 0 for all n. Because f x is identically 0, so all ordered derivatives of f x at x equal to a are also 0, and therefore C n is equal to 0. C n is f n a over n factorial. So C n is equal to 0 for all n and so on. So each coefficient of the series, the coefficient C n's, each coefficient of the series is also 0. Okay, let us consider the second order differential equation, x double dot plus x equal to 0, or we can say d square x by dt square plus x equal to 0. I will show how we can find the power series solution of this differential equation. So let us assume the solution of this differential equation to be x t equal to sigma n equal to 0 to infinity C n t raised to the power n. Okay. So let us assume that this power series is a solution of this given differential equation, which has got the radius of convergence r. So this series converges for mod of t less than r. Okay. Now and r is positive. So then what we will have, x dot t will be equal to sigma. Now the first term here is c naught. So when you differentiate that, it will vanish, and the terms will start with n equal to 1 onwards. So n equal to 1 to infinity n into C n t to the power n minus 1. Now we have seen that the series can be differentiated term by term in the region mod of t minus t less than r. So and it has the same radius of convergence. X double dot will be equal to sigma now n into n minus 1 C n t raised to the power n minus 2. Okay. And now n will start with 2 and go up to infinity. So now let us substitute, because x t equal to sigma n equal to 0 to infinity C n t to the power n we have assumed to be solution of the given equation. So let us substitute these values in the given equation. Then what we will have, sigma n equal to 2 to infinity n into n minus 1 C n t raised to the power n minus 2 plus sigma n equal to 0 to infinity C n t raised to the power n equal to 0. Here now what we will do, let us replace n by say j plus 2. Okay, n by j plus 2, then this will equal to sigma j equal to 0 to infinity, and then we will have j plus 2 j plus 1. So I can write j plus 1 j plus 2 C j plus 2 t to the power j plus sigma n equal to 0 to infinity C n t raised to the power n equal to 0. I can now change this summation over j to summation over n. Okay. So sigma n equal to 0 to infinity, and I can collect the terms. So n plus 1 n plus 2 C n plus 2 C n plus 2. Okay. And then I can write like this. Okay. So, what we will have now, we know that when the power series when the power series is when the sum function of the power series is identically 0 over an interval. So, here this is identically 0, this valid for all t satisfying mod of t less than r. So, every term of the series must be 0. Okay. So, when we take okay, so this will give you n plus, so t to the power n, the coefficient of t to the power n is equal to 0 gives n plus 1 into n plus 2 C n plus 2 is equal to minus C n, or I can say C n plus 2 equal to minus C n over n plus 1 into n plus 2. So, we can start with n equal to 0. When n is equal to 0, what we get? C2 equal to minus C naught, and then n equal to 0 gives 1 into 2. Then I can find C3. This relation is known as recurrence relation. Okay. So, this is recurrence relation. It can be recursively used to determine the values of the coefficient C n. So, for different values of n. So, when n is equal to 0, C2 we can find from here. This is minus C naught over 1 into 2, then C3 will be minus C1, n is equal to 1. So, we have 3 into 2 into 3, and then we can find C4. C4 will be equal to minus C2 divided by, we are putting n equal to 2. So, 3 into 4. And so this is further equal to C2 is equal to minus C naught over 1 into 2. So, we have minus 1 whole square into C naught, and then 1, 2, 3, 4. So, we have 4 factorial. Okay. Then C5 we can find, C5 will be equal to, when you put n equal to 3, minus C3 divided by 3 into 3 plus 1, that is 4, and then 3 plus 2 is equal to 5. So, we have and then we can get the value of say 5 in terms of C1 from here using this relation. So, we get minus 1 to the power 2, and then C3 is minus C1 over 2 into 3. So, C1 divided by 2, 3, 4, 5. Okay. So, what we get? This will be equal to 5 factorial, right, minus 1 to the power 2 C1 divided by 5 factorial. Now, so if what we get is, if we go on like this, we can see that C2k, okay, C2k will be equal to minus 1 to the power k into C naught over 2k factorial, and k will take values, k can take values 1, 2, 3 and so on, and C2k plus 1, C2k plus 1 will come out to be minus 1 to the power k into C1 divided by 2k plus 1 factorial. So, let us verify, we have written the values of C2k and C2k plus 1. Okay. So, you can put k equal to 1 here, C2 should be equal to minus C naught over 2 factorial. Okay. So, this is minus C naught over 2 factorial. When you put k equal to 2, then we will C4. C4 will be minus 1 to the power 2 C naught over 4 factorial. So, we get this is C4. Okay. And here when you put k equal to 1, you get C3 as minus C1 over 3 factorial. So, this is minus C1 over 3 factorial. Okay. And when you put k equal to 2, then you get C5 as minus 1 to the power 2 C1 over 5 factorial. So, you get this. So, in general we can write the value of C2k and C2k plus 1 from here, and once we have that, okay, but we have xt will be equal to, so then okay, xt sigma n equal to 0 to infinity Cn t to the power n. Okay. So, we will have C naught, so this series will be equal to sigma k equal to 1 to infinity minus 1 to the power k, if I take k equal to 0 to k equal to 0 to infinity minus 1 to the power k C naught divided by 2k factorial plus sigma k equal to when you take C naught and C1 are arbitrary. Okay, so k equal to 0 to infinity minus 1 to the power k, this t to the power 2k here, okay, because we are writing the value of C2k. Okay, so minus 1 to the power k into C1 divided by 2k plus 1 factorial into t raised to the power 2k plus 1. Actually, what we are doing is that xt you can split into two parts, in two series, sigma k equal to 0 to infinity C2k t to the power 2k plus sigma k equal to 0 to infinity C2k plus 1 t to the power 2k plus 1. Okay. One series will contain even powers of t, the other series will contain odd powers of t. So, we can write the series representing xt function in this manner and then put the values of C2k and C2k plus 1. So, we get this. Okay. Now, what we have is this is C naught times sigma k equal to 0 to infinity minus 1 to the power k t to the power 2k by 2k factorial, and then we have C1 times sigma k equal to 0 to infinity minus 1 to the power k by 2k plus 1 factorial t to the power 2k plus 1. Okay. And we can see that this series sigma k equal to 0 to infinity minus 1 to the power k t to the power 2k by 2 factorial represents the cosine t function, and sigma k equal to 0 to infinity minus 1 to the power k t to the power 2k plus 1 over 2k plus 1 factorial represents the sine function. Okay. So, x t is equal to C naught cos t plus C1 sin t. Now, if we note that in this example, in this particular example, we are able to write the solution of the differential equation in a closed form. We are getting x t equal to C naught cos t plus C1 sin t. Since it is a second order differential equation, general solution will have two arbitrary constants, and we have two arbitrary constants here, C naught and C1. So, it is the general solution. Now, in this particular example, of course, we have got the solution in the closed form, but in a general situation we will obtain power series that do not necessarily represent known functions. So, that is the remark I want to make. In our next lecture, we shall see more examples of differential equations, where we will see that the solution cannot be represented in a closed form. That is, the solution of the differential equation, general solution comes in the form of infinite series, which do not represent known functions, known elementary functions. Thank you very much for your attention.